No,
He's
ऐसा
busy
नहीं,
with
sir, this is not
admission
the
and
case.
नहीं, I understand.
examination, Dr. Bodla.
I understand. मैडम हम उसके साथ भी है टीम में एडमिशन में.
हाँ बिल्कुल.
Kanika also joined.
Admission and examination both are responsible jobs.
Yeah, that is true. Without admission, we are not there. We don't have any work.
Even sir, we have completed the final examination, online examination for B Form, D Form, and now we are going to start supplementary examination.
Very good.
Yes, for all this.
Yeah, actually, HRD notification is also there. All the final year students should be declared with their results by the end of this October.
Okay, okay.
Yeah, it's a HRD demand.
Sir, we are doing work. We are ready to publish the work, display the result. Our examination section is working on a fast pace.
Even DU also yesterday they have given a notification that they will be declaring this particular final year results by this time.
By the last 30th October, up to 30th October.
30th October and PG के लिए 5th of November दिए हैं.
Okay.
And हमारा PG का भी.
We are planning for second counseling also. Second counseling we will start almost 20th of October.
Actually हमारा PG का ऑनलाइन वाइवा के लिए भी नोटिफिकेशन आ गए हैं.
हाँ जी, हाँ जी.
वो भी करके खत्म करेंगे हम.
Right sir.
Actually QIP की वजह से थोड़ा वो भी
It's an ongoing process. All the processes are ongoing. It's a part of life.
Yes.
I cannot. अब टेंशन नहीं होती है. पहले टेंशन होती थी, अब टेंशन नहीं होती है.
Now we become immune to the system.
Good. टेंशन नहीं करना.
हाँ. तो अब तो ये है कि जो टारगेट, जो एम्स जो सेट किए हैं टारगेट्स, we have to achieve that set. We have to complete the work.
और कभी ये नहीं सोचना हाँ भाई आज काम नहीं है. हम ये सोचेंगे उसी दिन ज्यादा बड़ा काम आ जाएगा.
Should we start, Dr. Bodla?
Yeah, madam. You can invite.
Dr. Maninder is there.
Madam is there.
Madam is there.
Madam is there. Okay.
So we can start.
Ma'am, shall we start?
Yeah. Anushma.
Madam Maninder.
Oh.
Madam Maninder. She is there. Okay, ma'am. Should we start?
बिल्कुल मैम, बिल्कुल.
पूरी
गर्मी में बैठी हूँ.
Good evening, madam.
Sorry from our side, ma'am. अगर पॉसिबल होता है कि एसी हम वहां तक भेज सकते तो डेफिनेटली आज QIP के थ्रू हम वहां भेज देते.
So nice of you. Thank you so much. आज सुबह से right from 9 o'clock there is a power cut and we still don't know when the power will be back.
Oh, let us have our lecture very quickly. Madam, good evening, madam. Welcome to you.
Good evening, Dr. Bodla.
Anushma,
Sir.
start now.
Yes, ma'am. Yes, ma'am. Good afternoon to all of you. Now we will be commencing with our day 5 post-lunch session of AICT sponsored 35th QIP program. Now I would take the opportunity to introduce our chairperson, Professor Rajiv Tong, who is currently Dean of Student Welfare at Delhi Pharmaceutical Sciences Research University, New Delhi. He did Masters and Doctorate in Pharmaceutical Chemistry from Spear Jamia Hamdard, New Delhi, and has more than 30 years of teaching and research experience. His core area of research includes designing, synthesizing, and characterization of new drug derivatives, development and validation of analytical methods for drugs and drug formulation. He has also coordinated 4 MOUs with national and international universities and research institutes to promote the research activity in university. He has guided 24 MPharm students and guiding 7 PhD students and has more than 40 research and review articles in reputed national and international journals. He has organized more than 50 national including 4 international conferences and participated in more than 30 conferences with research paper presentation in more than 20 conferences. He has received appreciation award from Service Deputy Chief Minister Delhi Shri Manish Sisodia ji, Chairperson Medical Education and Health Service Committee Haryana Ms. Seema Tirka, and from Central Vigilance Commission for his valuable contribution in the field of pharma education and student related activities. Now I kindly request sir to kindly introduce our resource person.
Thank you,
Sir, over
Nishima.
to you.
Good afternoon, everyone. Today's speaker, Dr. Maninder Karan, we welcome you, ma'am, to this 35th QIP program organized by the DIPSAR by Professor Ramesh Vodla, Professor Manju Vyas, ma'am. Dr. Maninder Karan is a professor at Department of Pharmacognosy at Punjab University. She is the IQAC coordinator at UIPS. She did her PhD, MPharm and BPharm from Punjab University. She has more than 25 years of teaching and research experience and guided 7 doctorate and 21 postdoctorate students. She has authored more than 109 papers in national and international journals and has widely delivered lectures on various topics in pharmacy. Dr. Maninder Karan has authored and co-authored several book chapters and books, and she is also working as a reviewer for reputed professional journals. She has 56 monographs to her credit, and which 26 are pharmacopoeial monographs. She has filed 7 patents and granted 1 patent and transferred 1 technology. She was editor of the Pharmacos. She has completed 4 projects of Ayurvedic Pharmacopoeia of India and ICMR. And one of the most reputed project is the formation of Darvi gel as a proprietary medicine. Congratulations, ma'am. She is former expert member of Unani Pharmacopoeia Committee, Ministry of Health and Family Welfare, Government of India, New Delhi. Ma'am, we feel honored to be here as a speaker with us in today's session, and definitely our participants and the goal of this QIP will be achieved. So I welcome you, ma'am.
Let's welcome Maninder madam with a clap.
Thank you so much,
And
Professor.
in the situation of this, electricity is not there, still you are ready.
Yeah.
10 minutes
That's
ready.
true.
Again, I need
Actually,
Start your
to give a very,
with one hand she is managing
welcome
laptop
to
and.
Thank you, Professor Bodla, Professor Rajiv, Ma'am Manju Vyas, and in fact, I am equally honored to be part of this program.
Thank you.
And I feel myself as a very true member of DIPSAR and DIPSRU as well. And,
Thank you.
No doubt, ma'am. There is no doubt.
My sincere thanks to Professor Ramesh Goel, Professor Pathak, and Ma'am Manju Vyas, all the organizing team members for inviting me to this QIP program. So I would start with my lecture.
Yes, please, ma'am. Please start.
Okay, so I'll share the screen. Is it visible?
Yes,
Yes,
ma'am.
ma'am.
Yes.
Visible.
Okay.
Please continue.
Essentials of chromatography.
Yes, essentials of chromatography. In fact, just to go into a very little of why I selected this particular topic, as I was going through your brochure and flyer, I could see many eminent speakers. They have already delivered talks, and they have talked about variable aspects of phytopharmaceuticals, the advancements made, the development of phytopharmaceuticals, correlation between traditional drugs and phytopharmaceuticals and the modern system of medicine, and many other aspects. But I selected a topic which is very different from whatever you have been listening so far. I picked up the topic of chromatography, and it is not only you should say chromatography, it is talking about the basics and the fundamentals of chromatography. You see, in earlier times, most of the analysis were based on like titrimetry, gravimetry, spectrometry, and many other older techniques. However, with the passage of time, these techniques started getting obsolete, and some of them are even redundant today. And most of the techniques have been largely replaced by newer sophisticated and instrumental techniques, principally based on chromatography. So liquid chromatography techniques like HPLC and GC, they are now the principal and primary modes of estimation and analysis. And while a couple of other techniques, they are exclusively meant for isolation and separation purposes. So dear participants, if you happen to see, and I'm sure all of you have seen a good number of pharmacopoeias, if you see the monographs of these pharmacopoeias, you would realize that very few analyses are based on chromatography in the earlier pharmacopoeias. However, now chromatography has emerged as the heart of the analytical techniques. And HPLC, though it is last one in the series of chromatographic techniques to be developed, but this technique has emerged practically in every field of analysis, and both HPLC and GC, we say that these are the soul of separation analysis. No analysis in any field you will find which does not have HPLC, GC, or other related techniques as the principal methods of analysis. As far as the advancements are concerned, maximum advancements have been made in the area of HPLC, whether it is at the instrumentation level or it is in the column chemistry, new mobile phases, column chemistry, hyphenation techniques, and all that. And however, TLC, besides HPLC and GC, which earlier was used largely as a qualitative method, this has been recently accepted by USP as one of the official methods of quantification. So you will find that these chromatographic techniques, it is not that we are using them just in academic institutions or at the industrial scale. These are the techniques which are really a much part and parcel of the official organizations as well. So in nutshell, in today's time, it is just unthinkable of any analysis without chromatography at the center stage. Now, further to this, we do chromatography, we adopt many different techniques, and most of the times we do the analysis without knowing the importance of the basics, of the fundamentals, and the lack of fundamentals often lead us to a situation where we don't even know what we are doing. We don't even know whether we are doing the right analysis or not. We don't even know whether my results are correct or not. We don't even know what is the nature of the given sample. We don't know what to do if there are some such situations, what to do. Now, this is solely because of the reason that, number one, we do not understand the nature of our sample. We don't pay attention to that. When we know the nature of the sample, then what kind of operating conditions are required for that sample? What kind of stationary phases? What kind of mobile phases? What are the other operating conditions which are required to resolute, to separate, to purify, or to quantify a particular component? So my talk is today just to make my colleagues from different colleges and institutes, to make them aware of all those basic and fundamental aspects of chromatography, which would, I'm sure, help them whenever they are working in any of the chromatographic techniques to adopt a system which works well, which gives them the desired results, and they are able to analyze the sample in a right way. So with this background, why I have picked up this topic as essentials of chromatography, I'll just proceed to my next slide. So first of all, you have welcomed me to the QIP program of DIPSAR. I welcome you all to the beautiful world of chromatography.
Thank you.
So this is the world of chromatography, and it is self-explanatory. It is a beautiful world of colors. Going into a very brief history, it was in 1903 that Sweat coined this term. Chromatography principally means color writing. And he was able to produce a colorful separation of plant pigments through a column of calcium carbonate. So he named this technique as column chromatography, column adsorption chromatography. And this technique, which was developed in 1903, became popular many years later by 1930. Next came the thin layer chromatography, which was developed by using horizontal plates in 1938. However, a successful separation of terpenes was made by Minhard, and this technique became widely used once again about 10 years later in 1955. Paper chromatography. Martin, the king of the chromatography, he created paper chromatography in 1944. And just to share information with you all, that this is the only chromatographic technique which has won a Nobel Prize. This technique won Nobel Prize for Martin a couple of years later in 1952. Gas chromatography was developed by Creamer 1947, and it became widely available by 1960. GLC, once again, Martin is the person to develop GLC. And then came HPLC. It was developed around 1967 by Howard, Hubbard, and Scott. So this is a very brief history of the development of various techniques of chromatography. And now coming to understanding the basics. See, every analytical technique has its unique abilities. Same is true with chromatography. It has its own very unique abilities. And its unique ability is, which we cannot found in many other analytical techniques, is that besides this technique giving us a very diagnostic or qualitative information, it helps us to isolate the substance. It helps us to purify the substance. It helps us to quantify the substance. So chromatography has emerged as an analytical technique which has a set of abilities which are not available in many other analytical techniques. So although this chromatography simply means to write with colors, however, the term chromatography, it is not used independently, individually for different kinds of chromatography technique. Chromatography is a collective term for a set of laboratory techniques which is used for the separation of mixtures due to the difference in the distribution coefficient of sample components between two different phases. So this particular, you can say, introduction or what definition about chromatography, this is that it is a one single collective term used for all kinds of laboratory techniques. Now, what basically it is? It covers a broad range of physical methods which are used to separate or to analyze complex mixtures. It is a technique where both identification and purification can be done at macro or micro scale. Now, how does it work? It works like a magic. Here in this picture, you can see a beautiful spectrum of colors. And this spectrum of colors is that of a black ink, a dye black ink. And many of us would not be knowing that black ink is not a single black compound. It is made up of a number of different dyes, different color dyes in very specific composition. And when they are mixed together, they make the color black. Now, how do we come to know that what are those different dyes which make the black ink? Now, this is something which we cannot come to know using many of other techniques. We can't know it by, you can say, spectrophotometric method. We can't know it by filtration, centrifugation. कोई और मेथड नहीं है जिससे हमें ये पता चले कि ब्लैक डाई की कॉम्पोजिशन क्या है. But here is a technique which beautifully resolves those different dyes into separate spots, separate colored bands, and we are able to know how many components are there. So it is no less than a magic. Now, why is it so special? In any analysis, whether chemical or biological, whether we are working in a lab or we are working in an industry, there is always a need to separate the components from a complex mixture. Now, this is not only important, but is one of the most essential steps also in any kind of analysis. And today we have a large number of separation techniques, and one of the most basic technique is filtration. In filtration, what you can simply do is to separate out a solid from a liquid. Purification, isolation. Once again, you can separate out some purified solid compounds from a liquid form. Crystallization, same. Distillation, liquid from liquid. But chromatography is one technique which can separate a large number of complex mixtures with great precision. That is the beauty of this technique. It is not only that it separates the compounds with a great precision, even very similar components. For example, in case of proteins which may be differing just by, say, a single amino acids. Now, that is something we cannot analyze using most of the other techniques, but using a specific kind of chromatography technique, we can separate those closely related molecules. In fact, chromatography can resolve any substance, and that is why it is a very special process. Can not only purify or quantify, can also identify, and it is very selective in nature if we compare it with spectrophotometry. Now, coming to the theory, it is a separation method that exploits the differences in affinities and behavior between a mobile and a stationary phase so as to separate the components in a mixture. And the components of a mixture may be interacting with the stationary phase based on charge, relative solubility, or adsorption. If we go into the essence of these definitions, essence is same, meaning is same, but it is just the way each one of them is separated are distributed between two phases, one of which is stationary, the stationary phase, while the other is the mobile phase that moves in a definite direction. So this was the final definition given by IUPAC. Now, coming to what are the different types, the basic types of chromatographic processes. The principle stays the same. The application part or the practice of each one of them is different. It is either diagnostic, where we just need to know the purity of the given compound, or what is the composition, how many components are present in a given sample. When we are doing quantitative analysis, we need to determine the quantity of the given sample. And for preparative, we need to separate or isolate the components present in the given sample. So when we need to have a sound knowledge of the basics of chromatography, it is important that we select the right material as a stationary phase, moving phase. We must know what is the nature of the analyte and what should be the operating conditions. These are just some of the terms which we frequently come across. Mobile phase that flows over the stationary phase, stationary which remains stationary, does not move. Supporting is the media that supports the stationary phase, and eluate is the phase that contains the solutes. Now this is important to understand the mechanism, how actually it works. Now here, now this is a column of stationary phase filled with the stationary phase, and there is a mobile phase moving in one particular direction. Here we have a solute component. Now when this solute component comes in contact with the stationary phase and the mobile phase, it is continuously being acted upon by two forces. One is F1, which is hydrodynamic in nature, and this is the impelling force. This force tends to take the solute molecule along with it for movement, whereas F2 is opposite of F1. It is a retarding force, and this is on account of the molecular frictional forces, dipole interactions, and interactions within the stationary phase. These forces, these retarding forces, they tend to keep the solute close to the stationary phase. They don't allow the solute to molecule. So at any given time, when this solute is being acted upon by two forces, definitely either it will stay with the stationary phase, or because of F1, it will move along with the mobile phase. Now, why it will move with the mobile phase and why it stays just depends upon whether F1 is more than F2 or F2 is more than F1. If the interactions, the likability, the attractive forces between the solute and the impelling forces are more, it would move. It would leave its place of residence. However, if the retarding forces are more, it would like to stay back. It would like to reside with the stationary phase. So at any given time, it is being continuously interchanging itself between the stationary and the mobile phase. And when we are dealing with a large number of solutes, each molecule, each has its own properties, individual properties towards the stationary phase and the mobile phase. So when they are being acted upon by these two, they would behave differently from each other. जैसे forces, attractive forces or impelling forces change होती जाएंगी हर एक molecule के लिए, वैसे वैसे जो movement है वो change होती जाएगी. So this is basically the crux of the chromatography, that how actually it works. Okay. So in this case, whether the stationary phase is liquid or it is solid, there are two mechanisms which are playing a role. If it is solid, it is on account of adsorption. If it is partitioning, it is the partition coefficient which will determine what should be the likability and what should be the time of residence of molecule in the stationary phase. Now this adsorption, please, I would like to emphasize that adsorption is entirely different from absorption. Whereas in case of absorption, a substance penetrates into the bulk of the other substance. Whereas in case of adsorption, this is a surface phenomena where action takes place only on the surface of the substance. And there is a distribution between the liquid and the solid phase, which is determined by adsorption coefficient. When we are talking about adsorption, either there can be some chemical interactions between the molecule and the stationary phase. When it is a chemical interaction, we call this phenomena of adsorption as chemisorption. And chemisorption is a completely irreversible phenomena. That means if something chemically reacts with the stationary phase, and since it is irreversible, then we cannot get back that molecule from the place of residence. Desorption would not happen if there is chemisorption. So this is not required. Second is physical adsorption, which is a totally reversible phenomena. And this physical adsorption is an account of very weak forces of interaction, hydrogen bonding, electrostatic dipole interactions, and van der Waals forces. It is physical adsorption which actually works in chromatography, which actually designed in chromatography. Physical adsorption is followed by desorption. Desorption is just opposite of adsorption. In desorption, we tend to get back the molecules away from the stationary phase. And partitioning, it is a simple distribution between the liquid and liquid phase. So when the stationary phase is solid, phenomena of adsorption is happening. It is adsorption chromatography. When it is liquid, we have partition chromatography. And we have to classify according to the mobile phase. If the mobile phase is liquid, we call it liquid chromatography. If it is gas, we call it gas liquid or gas solid chromatography. Some other very common types of techniques are adsorption, partitioning, ion exchange, and size exclusion. This slide simply shows some of the examples of the chromatographic techniques based on liquid chromatography, gas chromatography, planar chromatography, and besides there are some other techniques. Now coming to, this is also some of the examples under different categories, same here. Now here you see that if it is liquid and solid, the separation mechanism is adsorption. In case of paper, it is both adsorption and partitioning. GLC, TLC, HPLC, UPLC, we can have a mix of the two, adsorption as well as partitioning. This is also in continuation to that. Now I would be moving on to some of the significant aspects. What are the actual factors which affect migration of a solute? Basically, we consider three factors. One is what is the nature of the adsorbent or the stationary phase. Second, what is the nature of the solvent or the mobile phase. And third is what is the nature of the solute. Now, first we take adsorbent. It can be either polar or non-polar. We must know what is the nature of our solute, and accordingly, we have to select either the polar or the non-polar adsorbent. The kind of interactions which are taking place with the polar and non-polar adsorbents are dipole, hydrogen bonding, or van der Waals forces. And a few examples we have of strong polar, medium polar, weak adsorbents like charcoal, silica gel, alumina, and a couple of more. Polar adsorbents are stronger than non-polar ones. This is a general feature that we must know, that if we are having a polar adsorbent, then it is so stronger than non-polar ones that we need to know what kind of mobile phase would be required, because it has strongly adsorbed, it has strongly taken up the molecules. So we need to have equally strong forces to dissolve the molecules. Now, this is some of the commonly used adsorbents. Silica gel, we have alumina at acidic or neutral pH, or we have at basic alumina. Then we have polyamides, cellulose, and okay. Now, besides the polar and non-polar, which determines the strength, another factor which is associated with the adsorbent is the particle size of the adsorbent. You all know that surface area is inversely proportional to particle size. As particle size decreases, the surface area increases. And when we increase the surface area, that means we are increasing the number of active sites which are available for interaction with the molecule. So when the number of active sites are increasing for interaction with the molecule, then the nature of the adsorbent becomes more stronger from a weak or a normal adsorbent. So I will just give you an example of particle size of silica gel, which is one of the most common adsorbent, and I'll just compare it with table salt, jo normal namak hum khate hain, that is of around 100 microns. Human hair, that is around 70 microns. Now, if you see for column chromatography, which is one of the more very commonly used technique, the particle size ranges from 60 to 210 microns. For TLC, it is normally 10 to 12. For HPTLC, 5 to 6. Nano HPTLC, 2 to 10. HPLC, 5 to 10. And UPLC is sub-micron, 2 sub-micron level, always less than 2. Now, silica gel is same. And if you have done any of these techniques, you will find that column chromatography, which has the largest particle size, this does not require much of the forces. Here, the surface area provided is much less than what is there in comparison to TLC. And that is the reason that same silica gel, when used for TLC, becomes comparatively stronger than when it is used for column chromatography. Same silica gel, when its size is further reduced for HPTLC or for HPLC, the particles are so fine, they are so closely packed that now we need to apply some additional pressure for the mobile phase to pass through those closely packed columns or closely packed stationary phase. So that is the reason that same silica gel, when we move from column chromatography to UPLC, in column chromatography, the solvent just flows on its own without any force. It comes down by gravity. In TLC, HPTLC, it rises against the gravity. However, in HPLC and UPLC, you have to apply pressure, reasonably high pressure for the solvent to pass through. Then moisture content, besides the nature of the adsorbent and the particle size, moisture content is another factor. If moisture content in the given system is present in the range of 10 to 20%, it would act largely as a partition system. And a moisture in the range of just 4 to 6% makes the system suitable for adsorption. And that is the reason that when you have TLC plates and we prepare them in the lab, we normally activate the plates. If you don't activate the plates, you just prepare the plates, air dry the plates, and you run the chromatogram, you will have entirely different results, because then a lot of moisture going up to 20% is likely to be present in that silica gel layer on TLC plate. And then it would be acting less as a stationary phase, as a adsorption phenomena, more as a partitioning system. But when we activate the plates, we tend to get rid of the moisture. We activate the plates for almost half an hour at 105 or 110 degrees centigrade. So आधे घंटे में जब हम plates activate करते हैं, and when we take these plates out, then from the atmosphere, silica gel has the capability to again take up some moisture, but then it does not exceed more than 4 to 6%. And 4 to 6% free moisture does not alter the system from adsorption to partitioning. So then the TLC plates, they act as adsorption system. Then is the nature of the solvent. The power of elution depends much on the polarity of the solvent. In 1940, Traps gave a list of solvents which can be used in chromatography, and he listed these solvents according to the eluting power. Now here you see, as you move down from light petroleum to down to water, pyridine, and acetic acid, you will find that eluting power increasing. Light petroleum, which is most nonpolar, has the least eluting power. As we move down, we have some medium polarity solvents like dichloromethane, chloroform ether, and still on downside, we have propanol, ethanol, water. So when we add these polar solvents to the system, we are basically increasing the polarity of the system. So it is important now, I talked about the stationary phase, that if we are taking a polar stationary phase, which is a strong one, then it would retard the components so strongly that it would not allow them to get eluted if you are using a non-polar solvent, because they have least polarity, they have least power to take out the components from a strongly adsorbed system. तो अगर एक strongly adsorbed system है, हमें वहां पे equally strong polarity का solvent चाहिए होगा, mobile phase चाहिए होगा उनको elute करने में. And this is the practice all of you must have come across. When we run the TLC, we see that everything remained at the base. वो move ही नहीं किया, TLC पे कुछ develop भी नहीं हुआ, or everything moved to the top. Nothing could be resolved, everything moved to the solvent front. Or if at all it moved, we did not get any separate components. There was just one large, you can say, a band, which did not tell us what it is. So why we are getting that? We are getting that because our selection of the mobile phase vis-a-vis stationary phase, taking into account nature of the solute, was not correct. Then nature of the solute itself is very important. Molecular weight is the first feature of the solute. It is governed by the Traub's rule and the reverse Traub's rule, which tells us about the relationship between the molecular weight and the adsorption. Now, according to the Traub's rule, as the molecular weight increases, the adsorption increases. Now, this is true only for homologous series. Adsorption increases when the molecular weight increases. And this is applicable to largely non-polar adsorbents, where the principal forces of attraction are the London's dispersion forces and van der Waals forces. This rule is reversed and is known as reverse Traub rule when we are using polar adsorbents. On such adsorbents, the interactions are due to polar groupings on the solute and the adsorbent, and the remainder of the molecule plays a very little part in the process, except that it just modifies the electronic configuration of the polar groups. The side chain present on the molecule acts as a diluent for the active group, and जितनी बड़ी साइड चेन होगी उतनी डाइल्यूशन होगी, उतना एड्सॉर्प्शन decrease hoga with an increase in molecular weight on account of an increase in the length of the side chain. However, if the solute is polyfunctional, then there are three different factors: the number of the functional groups, the spacing of the functional groups, and the molecular configuration of those groups, which will make the process little complicating for us to determine what should be the selection of the stationary phase and what should be the mobile phase. It is not that the number of the constituent groups, the nature of the constituent groups further has an equally important role. Brookmans gave a classification that when we move from hydrogen to carboxyl, you will find there is an increase in the affinity, or if we move down from carboxyl, hydroxyl, amine down to H, the affinity decreases. Means on one, just imagine one single molecule, there is a simple substitution is just H, the affinity of that molecule vis-a-vis if on that particular carbon or that particular position we attach, say, hydroxyl, the affinity would be entirely different. And if we replace that with, say, carboxyl, rest everything is same, the affinity would be different. So accordingly, we have to know what is the nature of the constituents groups. Then unsaturation, you know, when we are dealing with organic molecules, unsaturation, saturation is a very important component. And unsaturation in a molecule leads to more adsorption. And this is just because of the greater electronic density, which is associated with the pi orbital electrons of the aromatic molecule. So same molecule, if there is saturation and if there is unsaturation, there would be a tremendous difference in their affinity towards the stationary phase using same mobile phase. And this is what we call as the rule of triangle, that how we should select the mobile phase and the adsorbent. Here you see, I take, this is the solute. It can be either polar or non-polar. What should be my adsorption phase and what should be my mobile phase? If my molecule is polar in nature, then the adsorbent selection has to be towards the strong adsorbent. If it is non-polar, then see here, it has to be weak. Once we have selected the adsorbent, depending on the nature of the molecule, now comes the mobile phase. When we are using this, a strong adsorbent, the mobile phase has to be polar one. If we use non-polar mobile phase, you will not be able to eluate or resolute any of the compounds. And if the adsorbent is weak, we have to use a non-polar solvent. This is what is called as a simple rule of triangle, which helps us at first place to know how we have to select the adsorbent and the sorry. Okay. So this was in general about the chromatography, and since paper chromatography is, I would be talking just few lines about paper chromatography for the reason that many of you might not be knowing that paper chromatography is one technique where both adsorption and partitioning phenomena takes place. Here, the stationary phase is nothing but a paper, which is a very high quality paper made of pure linters, and where the alpha cellulose content is more than 98%. They have very smooth surface where all fibers are oriented in one direction. Now here, the cellulose of which the paper is made up of, that acts as the stationary phase for adsorption. And this cellulose is holding the loose moisture. And that moisture, which is held loosely by the cellulose, that provides a small platform for partitioning. So in case of paper chromatography, that is the reason that both adsorption and partitioning phenomena are taking place. Otherwise, for rest of the things, that what is the nature of the components, how we have to select the mobile phase, those rules stays the same. This is just a small introduction about what is the normal and the reverse phase chromatography. In case of normal, the adsorbents are polar and the mobile phase is non-polar. And in this case, the non-polar components elute first. However, in reverse phase, which is the most widely used technique in pharmaceutical analysis, the adsorbents are non-polar and the mobile phase is polar. And here in this table, you can see the stationary phase is polar in normal phase, non-polar in reverse phase. Mobile phase is reverse of the two. The compounds that elute first are the non-polar in normal phase and polar in reverse phase. And the compounds that elute last, polar in normal and non-polar in reverse phase. And these are some of the examples of the normal and reverse phase silica gel. Normal silica gel is a normal phase, and C4, C8 kind of bonded phases are the ones which are used in reverse phase. Here I just show you, this is a normal silica where these gray, these are the silanol groups, and these are the silanol groups, silica and silanol groups which are attached to it. And here you see what we call as the bonded ones. There is a hydrocarbon chain when attached to the silanol groups that makes it a bonded phase. If one hydrocarbon chain is attached to one single hydroxyl group, we call it as monomeric. And still then we are left with a couple of the free hydroxyl groups. And when these are further bonded by small chains, then what we call it as the end capping. And when these hydrocarbon chains, they are manufactured in a way that each hydrocarbon chain is attached to two of the silanol groups, we call it as polymeric. And similarly, for end capping, the arrangement that one molecule is able to attach to more than one molecule, we call it as super end capping. So chromatogram, irrespective of the technique, it is a visible record or visual output which shows us the results of separation. And fingerprinting, it is a graphical representation of the inherent characteristic properties of a given mixture, and it is determined by its chemical profile for pharmacologically active or chemically characteristic constituents. And now just some of the common troubleshooters that you must have come across. If there is over migration, the reason is the developer is too poor, and the solution is reduce the polarity. If there is under migration, the developer is too non-polar, that means increase the polarity. If there is a distorted solvent front, that means the developer was not equilibrated fully. Solution is first to equilibrate. If you get distorted spots or peaks, adsorbent's choice was wrong, number one, or the concentration of the or the amount of the applied sample was too much. So if adsorbent is wrong, change the adsorbent. If concentration is too much, dilute the sample. If there is no separation at all, then both developer and adsorbent both are wrong choices, and you have to change both. And if there is a tailing, either the sample applied is too much, there is overloading of the sample, or it is the nature of the components, which could be either basic or acidic or some specific kind of molecules, then you have to either reduce the concentration if there is overloading, or you have to increase the acidity or basicity of the mobile phase, or you can select the stationary phase accordingly. Then couple of advantages which of course all of you are well aware. I would say that chromatography is indispensable in modern pharmaceutical research, analysis, and quality control. And you will find that USP has more than 3,000 monographs where chromatographic purity and assay methods are based on just HPLC. So it is vastly used technique for pharmaceuticals, biochemicals, petrochemicals, forensics, herbals, industrial chemicals, environmental pollutants, clinical medicine. You just think of any area and you will find chromatography there. So a wide range of applications further in continuation to that, where you can do the quantitative assay of drugs in formulations. Then for biomarker research, identification and characterization, stability is an important part where we use these techniques, metabolism studies, then qualitative and quantitative analysis, food products, herbals, environments. And in last, I would just conclude by saying that in this session, what you learned was the basics of chromatography, including what is chromatography, how it works, principles and mechanism of separation, what are the factors that influence separation, and a brief outlay of different techniques, stationary phases, including normal and reverse phase, common troubleshootings, and general applications. And with that, I would congratulate you that you have completed the basic knowledge in chromatography. So thank you. And thank you once again, the organizers and the participants as well.
Thank you, ma'am. Thank you so much for a very enlightening and I can say a thoughtful lecture. And in a simple language, I can say that you have covered all the aspects of chromatography in a single lecture. I think it is useful not only for the BPharm students, it's useful for the BPharm, PhD, and postgraduate students also. So in a single lecture, they can get so many things you have covered that I'm very much happy that you have covered this troubleshooting. No, many of times the students face these kinds of problems and they ask from their supervisor that, sir, if there is a over migration, there is a lower migration, that what should we do? So you have covered this aspect, and even that particular triangle, that's very, very important. That's why very important that how to select the solvent system. Because when we are going for a TLC in a lab, because in HPLC, HPTLC or UPSLC, we need some skills. Handling those instruments is not so easy. But TLC, paper chromatography, I can say these are the simplest one, and these are the methods which we can use in either in pharmaceutics, in pharmacology, in all the departments. I can say that we can use these paper chromatography and TLC for analysis purpose in a short period of time. So thank you very much, ma'am. And from the participants, please, you can ask question. Now the panel is open. You can ask question. Is there any question from participants, please?
Otherwise, madam has given very detailed.
Yes, No doubt, ma'am.
lecture about chromatography. Very basic things.
So this was just basics, and in the next lecture, you are going to listen about equally high advancements of HPLC.
Madam, basic
Or ma'am,
basic
we
ही पता
will
होता
wait
है.
for that, ma'am. We will wait. Definitely. And in this situation, you have given a wonderful lecture, ma'am. Thank you very much. Please give a big round of applause for her.
Thank you so much. Thank you.
Participants, if you have any question, madam will be ready. Madam is ready to answer you. Do you have any question? Any participants?
I could see Dr. Pathak, Professor Pathak, and good afternoon, sir. And Mahavir is also there. Happy to see you, Mahavir.
Thank you, madam. Thank you. Thank
How
you.
are you?
Pathak sir has also joined.
Yes, I could see Dr. Pathak also.
So,
If there is no questions from the participant, then I would like to request Professor Rajiv Tong to kindly present e-certificate to Maninder ma'am, and ask Mrs. Manju Vyas ma'am to kindly share e-certificate.
Please
okay,
share.
just a minute.
Ma'am, due to this pandemic COVID-19, we are presenting you the virtual certificate. So please accept from our side. And thank you very much for your lecture. Please.
Thank you. Thank you. It's my pleasure.
Thank you. Thank you very much.
Thank you.
Thank you, ma'am.
Namaskar.
You have
Namaskar,
delivered
Dr.
without electricity,
हाँ जी मैम उसी के लिए
without fan.
डॉक्टर साहब वेट तो कर रहे हैं बट इफ यू गिव अस 10 minutes I think we should better
No, ma'am. You can take 10 minutes. You can take.
He says he will continue like me only without power.
So nice.
No, ma'am, if you are not comfortable, we can start.
Madam,
After
he
10
feels,
minutes.
Please take your time.
madam, he
Please
is
take your
feeling
time.
that you are
It's
his
fine.
power.
He says it's fine.
Okay, then it's okay, ma'am.
Oh, it's okay.
Okay. Thank you so much.
Thank you,
you.
ma'am.
Thank you, ma'am.
Thank you. Thank you, ma'am.
Thank you, ma'am.
So next speaker is, yes.
Sir is joining from the same Dr. Karan Kashish. The same speaker. Ma'am.
I think with the same window, I think.
He will join.
Ma'am, has second resource person joined?
Yeah.
Just a minute, Anushma. He is joining.
He joined.
Okay, ma'am.
Stop sharing.
Joined, madam.
Sir has joined?
Yeah. Maninder, by name Maninder has joined.
Now I would like to request Professor Rajong to kindly introduce our second resource person.
Yes. Thank you, Nishma.
Raju.
So over, yes.
Dr. Raju, let Dr.
Shall I wait, sir?
Just a minute.
To respond.
Okay.
Karan to respond. Dr. Karan.
We will wait.
Dr. Karan.
Wait, Dr. Bodla.
Yes, I am there.
Oh,
yes, sir.
Okay, sir.
Good afternoon to everyone.
Thank you, sir. Good afternoon, sir. And
Very
we
good
welcome you,
afternoon,
sir.
sir. दिखाई नहीं
nice
दे
to
रहे
see
आप
you, sir.
मिठाई भी पाठक साहब दे रहे हैं
दिखाई नहीं दे रहे
सुनाइए क्या हाल चाल है
फाइन आप सुनाइए सर so kind of you for accepting.
Thank you, it's always pleasure.
Good afternoon, sir.
Good afternoon.
Sir, we welcome you in this 35th QIP program at DIPSAR. From our seniors and as a chairperson, I welcome you from the heart, depth of the heart, sir. So please give a big round of applause for Dr. Karan Kashish. Sir is working as professor at Department of Pharmacognosy, University Institute of Pharmaceutical Sciences, Punjab University. Professor Vasist has worked as a scientific advisor to United Nations Program on Medicinal Plants for 6 years and coordinated United National Program visiting Global Medicine Plant Institutes. He is the ex-member, Ayurvedic Pharmacopoeial Committee, Scientific Body of Pharmacopoeial Commission for Indian Medicine, Pharmacy Council of India, All India Boards of Pharmaceutical Education, AICT, and is the former president of Punjab chapter of Indian Pharmaceutical Association. He did his PhD M.Pharm, B.Pharm from Punjab University. He has authored more than 100 research papers in national and international journals. He has visited more than 15 countries and has widely delivered lectures on various topics of pharmacy. He has contributed more than 55 monographs to Ayurvedic Pharmacopoeia of India and in Quality Standards of Indian Medicinal Plants published by ICMR. Dr. Vasist has authored and co-authored several book chapters and books and is also working as a reviewer for reputed professional journals. He has more than 35 years of teaching and research experience. He has guided 9 doctorate and 37 postgraduates. He has filed 4 patents and granted 1 on novel molecules from a plant source. He has completed 5 projects of Ayurvedic Pharmacopoeia of India, and one of the most reputed project is formation of Darvi gel as a proprietary medicine. We congratulate you, sir, and again I welcome you as a chairperson. So please, you can start your presentation. Thank you very much.
Okay, thank you, Professor Rajiv. It's pleasure always helping my colleagues and sharing the knowledge that we gained all through our life. And now, can I start with the
please start, sir.
Yes.
Please start.
Yes.
Yes.
So I have to share the whole screen.
Yes, sir.
Yes, sir.
Okay, so is it visible? Is it the screen only that is
sir,
visible?
At the bottom there is a green mark, that's share screen. From there you can.
Okay.
Yes.
Okay, is it right now?
No, sir.
No.
Still it is not visible.
Click it, sir.
Okay, let me see. Yes.
After that, click your present.
Okay.
Yes.
Now
Yes. It is starting, sir.
Okay. Okay, thank you. As I have been told, I am to speak about HPLC, and then in the end, I will cover up its applications in the phytopharmaceuticals. And this is a brief outline of my presentation. And I do not know how much I will be able to cover, because normally we are spending 3-4 lectures for covering all this. So I will be moving very fast, and if anyone has any request, I can stop there and explain in more details. So we will be taking HPLC as a technique, very little about instrumentation, more about the column characteristics, mobile phases, and then probably most part I will be spending on characteristics of a good chromatogram in HPLC. And then in the end, I will discuss brief applications of HPLC in phytopharmaceuticals. So this you already listened to, and Dr. Maninder was telling that it was IUPAC which gave definition of chromatography in 1993. So HPLC is one of the technique of chromatography. And I would like to run this video, which have taken from the thermo, and it's a beautiful display of HPLC. So it shows you the column. Now the mobile phase blue is flowing, and then you inject the sample which goes from the one side of the column, all molecules inside in one go, and then as they are moving, they are getting separated. Some are moving fast, other are moving slowly. And here you can see the time elapsed. So different kind of molecules, they have now they separated, and the red one, which had least interaction with the stationary phase, they are exiting the column. They are going to the detector, and the bottom you see the response. So here on x-axis we have the time elapsed, and on y-axis we have the detector response in millivolts. So in brief, this is how the HPLC works. And the capability of the HPLC is, if you can dissolve the components, you can resolve them also. And all mechanisms which are operative in separation in chromatography are made use in HPLC also. So from here, I move on to very brief about the instrumentation. So these two systems, one you see modular one, which we acquired in the institute in 1986. At that time, it was something like buying your own jet in today's time. And on the right-hand side, we have the presently made Waters instruments, which are more integrated, and you don't see anything from outside except the small computer portion. All HPLC systems, they have these 5 parts. So we have pumps, injector, column, detector, and we have a data processing unit, which is handled by the software. So to start with, first part of the HPLC is pump. Earlier, the pumps used to be of binary type, which means in normal working HPLC unit, we were taking 2 pumps, although it was possible to run the system. So pumps, and 2 pumps will take feeds from 2 reservoirs, and it will go to the mixing chamber and then will be delivered. And the modern type pumps are quaternary pumps, which are seen on the right-hand side. They can take feed from 4 reservoirs, and there's a proportionating valve where you can mix them as desired, the 4 solvents, and the same single pump then pushes the desired proportion of these 4 solvents into the system. And the basic purpose of the pump is to deliver accurate flow and working with precision, irrespective of what is the pressure ahead of the pumps. The earlier pumps, they were meant to, they could tolerate pressure of up to 1,000 pounds per square inch, and now 15,000, 20,000 is very common. Already companies have discovered the pumps which can withstand the pressure up to 50,000, and there was one article which said that even 150,000 pounds per square inch pumps are now available. And the most part, I would say, in construction of HPLC unit, the pumps take a lot for in terms of value and also in terms of innovations. Then after the pumps is the injector. The role of the injector is that without disturbing the flow, you are able to inject the desired volume of your mixture which you want to separate. So this is a diagram of typical rheodyne injector, which used to be earlier used in these systems, but now you have auto injectors which are built in 2 positions. That this black knob, it has load or inject position. If you rotate to the left, it goes to the load, and in this position, your loop, which is at the back, is cut off from the system. You can inject your sample, which is shown here as a yellow, color, and then when you rotate the knob to the inject side, this yellow injected material goes into the system. So these loops are changeable, and you can have any size loop. And if, for example, you are using 20 microliter loop, maximum that you can inject is 20 microliter, which is normally recommended that the loop should be used with full capacity, but otherwise you can inject quantities less than 20 microliter. There comes the next component, which is the column. Actual chromatography happens in the column. Pumps, they only help to push the mobile phase. Injector only helps you to inject your sample into the system, but the chromatography happens in the column. So the column is nothing, but it contains a stationary phase, which is filled into the stainless steel tubular structure. And since these particles of stationary phase are fine, it's like pushing your liquid through clay bed. That means you have to push it very hard, and otherwise if you are pushing it through the sand, it will take less pressure. So it's the same phenomena here. Depending upon what is the particle size of the stationary phase, accordingly the pressure would be exerted to the movement of the mobile phase. But the pumps here have the role that they have to always working and maintaining the same flow rate of the mobile phase with precision. So after the components, as I shown in that small video, once they separate into different components, they move on to the detectors. And detector is a component which detects whether the molecules are, so we have the electricity now. So this, these detectors, the role of these detectors is whether the mobile phase is neat or there are some components flowing in the mobile phase. And these detectors, they are categorized fundamentally into two categories: bulk property detectors and solute property detectors. The bulk property detectors detect these molecules when the response is proportional to the number of molecules. It's like colligative properties in pharmaceutical chemistry. And it does not consider any characteristic of the molecule. So irrespective of what kind of molecules are flowing, it would only be sensing the number of the molecules passing through the detectors. Whereas the solute property detectors, they consider the number as well as the characteristics. Like in case of UV detectors, whether the molecules are strongly absorbing or they are absorbing feebly, accordingly the response would be high and low. So it depends on the molar absorption of the molecules. That means fundamentally the solute property detectors, they consider the basic characteristics of the molecule, and most detectors that we commonly use, they fall in this category. And we have UV detectors, photodiode detectors, electrochemical detectors, fluorescent detectors, luminescence detectors, whereas refractive index is very commonly used bulk property. And we have evaporative light scattering detectors, conductivity detectors, charged aerosol detectors. But probably if you consider RI, UV, PDA, that covers most detectors used in the pharmaceutical industry. So this is the slide showing you the sensitivity of the various detectors. Of course, on top we have the fluorescence detectors, which is also very selective. So that's the beauty of the fluorescence detectors, that not only sensitive, they are selective also. And most bulk property detectors will fall onto the lower side, and their response or their sensitivity is comparatively less. Then the response generated in the detector, it goes to the data management system, which in modern time is nothing but the computer, where a particular software handles this response coming from the detector. Not only this data management, it also has the capability to control the functioning of all components of the HPLC. So modern HPLCs, they are internet enabled, and the beauty is that you can control the functioning of these machines from your home also. In the midnight, if you feel like changing the sequence of your analysis, you can do it. So that is what is the advancement. And I remember earlier days when every 30 minutes you had to go to the machine and inject the sample and then wait for 30 minutes giving the next injection. So now, as I told you, these different parts, what you change, you don't change the pumps. They are required at, with the machine and they stay the same. You don't change the detectors. In the initial time, either you buy one detector, or if you have funds, you buy the 2 detectors. But what you normally change is the column where actually chromatography takes place. And columns, they have undergone so much of changes that it is really very difficult to keep pace with the emerging chemistries in the columns. So with respect to columns, one, their size is important, where we consider the length and the diameter. Then the packing material, that is the nature of the stationary phase, what is it? And then the morphology of the stationary phase. So these are the key characteristics which define the column, that what kind of column it is. So if you see this slide, you have all kinds of columns from very mini size, very large size, which are used at process scale. They are categorized. In the third place, you have the analytical columns, which are normally from 1 millimeter to 4.6 millimeter in diameter. And in length, it is 1.5 centimeter to 25 centimeter. And as you go up, you have reduction in size. We have capillary, nano. And if you move to the bottom, we have larger dimension columns, which are used for isolation scale, for preparative purposes, and even in the industry for expensive drugs. The another point to be noted here is that the particle size of the stationary phase in analytical columns, if we consider the modern times, probably 5 micron would be one which is average. But most users now, they are shifting to lower than 5 micron. And then with semi-preparative, this size increases. It increases further with preparative at process scale. So with respect to the packing, most of the time we are using Silica, which is probably must be covering more than 95% of columns. But we have alumina also. We have, yes? Is it fine?
No, sir, it's fine. Please continue. It's fine.
Okay. Polymeric stationary phases. Then we have the recent advancements where we are using the synthetic silica, but the synthetic silica is containing organic component in the form of methyl or ethyl functionalities inserted into the basic skeleton of the silica. This diagram shows you the normal silica. Normal silica is basically silica linked to oxygen and hydroxyls, and we have metallic and different kinds of hydroxyl groups which actually works for the chromatography. So you can divide them into different categories based upon their acidity. The least acidic are those which are associated, and we see them in green color in the top. And then we have the blue, which are located on the same silica atom, and then the yellow, which are free. And the most acidic are where the hydroxyl containing silica atom is linked to the metal ion. Now, in case of modern silica, that's hybrid silica, you can see here how the changes are made. So some of the linkage which earlier was through oxygen, they have been changed with CH2 groups.
Participants are requested to mute themselves.
Then moving further, we started with the normal silica, which was natural silica. So natural was containing hydroxyls, and these hydroxyls were responsible for interacting with the molecules. But now we are more into the synthetic silica, where this silica is synthesized, and either it's pure or it is hybrid, as I told you. And then in derivatized forms, instead of hydroxyls working for the chromatographic function, there are different kinds of functionalities which have been inserted onto those hydroxyls. And these are shown here as C18, C8, phenyl, and then we have shield reverse phase column. If you see them, linked to the main core of the silica, either through one bond that is in the bottom, which we say monomeric, or by 3 bonds, which we say polymeric. And in replacing the hydroxyls with these derivatized forms, it's never 100% complete, and what is left, we normally tend to block those hydroxyls. We say these columns are end caps. So these terms, the reverse, these are the derivatized silica columns containing different functionalities, and probably the most common columns that we use are C18, C8, and phenyl. And then moving on, you have many more functionalities which are linked to the basic skeleton of silica. In fact, the chemistry of silica has been so well understood that now practically you think of any molecule, it's possible to link that molecule to the basic skeleton of silica. So rather than hydroxyls working for chromatographic separations, here you see these functionalities that have been inserted onto those hydroxyls function as the medium of chromatographic separations. And still we have more types of the columns. So this explains you that to run your system, you need basic understanding, and probably let's say another chapter or another understanding, but we have a very wide and diverse kind of stationary phases which are suited for one or another kind of separations. And based upon our goal, we tend to pick up the desired kind of the columns. But if someone, for example, is going for the purchase of HPLC system for the first time, probably C18 is the one column which the manufacturer supply, and C18 probably would also be getting to more than 50% of the analysis. So that is with respect to what is present, its nature of the stationary phase, and then history of the stationary phase, and then is the basic morphology of the stationary phase. That on right hand side you see the lower one, the natural silica, which was crushed and passed through the sieves, and then appropriate size taken, but still it was irregular in shape. And on top you see the man-made silica, which you construct in the form of the beads, the same kind of bead you saw in that demo which I showed you of thermo. And then the size it weighs. Now you can synthesize silica in any size that you want. 5 micron is probably common, and we are moving less than 5. So 3.5 is probably very common now, but 1.7, 2, this is reserved for the modern machines. 10 at one time, there used to be one column of, I remember, of Waters by the name Bonaparte that was so famous, and it ruled the chromatography for practically 2 decades. And now you are not using that. So as you reduce the size, you increase the efficiency, which is shown here in plates per meter. And this high number indicates that the smaller size particles are more efficient. Further, you can construct them in the porous form or non-porous form. Porous form mostly used in analysis, and it's also used in separation based on the size of the molecules. So these pore sizes, they can be constructed into different dimensions. This slide shows you the characteristics of basic stationary phases. We have silica, hybrid, lumina, and then these polymeric stationary phases. But if you see the silica, you will mostly find 3+ except for the pH. So silica is both on acidic pH and alkaline pH. Is not very good stationary phase. So that partially has been overcome by using the hybrid technology. So this is just to give you an idea that how the size has been reduced, human here in the center, and you can compare it what is the 1.7 micron silica particles look like. So this slide shows you the chromatogram, which has been developed using different sizes of the stationary phase. The top one is 5 micron, 3.5 micron, and bottom one is 1.7 micron. Now, if you see the analysis run time, it's 10 minutes, reduced to 4 minutes, to 2 minutes, to 1.1 minute. So you can see that how much you gain in terms of time and also in terms of efficiency, if I am to, because they have been 1.10 minute has been taken into the same scale as is the 10 minutes. That means in comparison to these peaks, the peaks in the lowermost chromatograms are much more efficient. That means their plate count is much higher. So in all respects, you have used very little time, and you have improved the analysis also. So these columns, normally we divide them into normal phase columns or reverse phase columns. And there is a situation when you have to use the normal phase columns, but not normally used now. And most often used are the reverse phase columns, where C18 is probably the most common, followed by C8, and cyanocoil is used in normal phase also and in reverse phase also. And probably its use in normal phase is more common than in the reverse phase. And then you have various other kinds of columns. So this slide shows you the relative uses of different kind of columns. So if you see the C18 is 39, C8 is 26, then cyanopropyl in normal phase is 14.5. If you sum up this probably mostly covers the entire spectrum, and adding another 12% of phenyl column, which is very well suited for particular API moieties. So then moving on to the mobile phases. For now, reverse phase, water is the main component, and we use modifier either as methanol, estronitrile, or tetrahydrofuran, or the combination of these. And I don't go into the details of the capabilities of these mobile phases. And methanol adds less strength, estronitrile adds more strength, tetrahydrofuran still adds more. In normal phase, the same series that Madam must have told you is starting with hexane, moving on to the alcohols, you increase strength of the mobile phase. So this is in brief about the parts and the stationary phase and the mobile phase. Now, the most often students, they get the chromatogram, and if they are able to get a good peak, they would assume that their chromatogram is very good, which is not the case. There are certain characteristics which must be taken into consideration to say that whether your chromatogram is good or okay or is not acceptable. And those characteristics are retention factor, selectivity, efficiency, resolution, peak symmetry, or tailing factor. So these are the parameters which one should be aware of when doing the HPLC, and your chromatogram must pass for these parameters. So now we consider these parameters. First is the retention factor or capacity factor, which in fact tells you how strongly your molecule interact with the stationary phase. Now, a mesocyanic component which does not interact with the stationary phase, and it flows over the stationary phase as if there was no stationary phase. So it will take time equivalent to the void volume of the system. Let's say if the void volume is 2 milliliter, from injector point to the detector point, which takes into consideration the volume in the connecting tubes, wide volume in the column, and the flow cell volume. So this component, which does not interact, it will be shown in the detector at 2.5 minutes if we are maintaining 1 mil per minute of the flow rate. That means we say it will take 1 column volume to transfer this component from injector side to the detector side. So column volume we say because this 2.5 milliliter, which I said is the wide volume or the dead volume, it is largely contributed by the column. 80–90% of this comes from the column and the rest from the tubings. So that means when we say 1 column volume, we are referring to the wide volume in the system. So this capacity factor is calculated by seeing how much volume of mobile phase has passed through the system before the component was detected by the detector. And on the bottom, you see the formula. For example, the second peak on the right side, if you have to calculate the capacity factor of this, V2, so V2 is the volume that has been used for transferring this component from injector to the detector, minus V0, that volume which is only the dead volume, minus V0. So that means for this peak, it becomes 0 because V0 minus V0 divided by V0, this becomes 0 value. And for this, it becomes 1 because these figures or these peaks have been so arranged that it's a 0 volume. That means to transfer this peak, we are using 1 column volume. To transfer this, we are using 2 column volumes. And for this, we are using 3 column volumes. So that means if you are getting a peak somewhere very near to this 0, that means your component is not interacting with the stationary phase. And we do not accept such kind of analysis. And imagine another scenario where after 30 minutes, you have your component in the detector, and time at 1 milliliter per minute, push 30 milliliter of the volume of mobile phase. So that means that is 30 minus 2.5 divided by 2.5, that would be the capacity factor. And we do not accept that also. So what is the ideal capacity factor? Where it should be the 2 to 7 should be the value. That means somewhere from this point onward till you have the 7 column volumes used is the right kind of interaction of our analyte molecules with the stationary phase. So that is retention factor or capacity factor. It's only the measure of how strongly the analyte molecule is retained by the stationary phase. Now to increase or decrease this, if for example it is very low value of capacity factor, you want to increase this value, that means you will decrease the strength of your mobile phase and vice versa. And you can, if for example with changing the mobile phase composition it does not serve, then you choose the second chemistry which is less interacting with the component. So that means the choice of column chemistry and increasing or decreasing the bond strength will allow you to be. Then second parameter is the selectivity, which I take at the same time, and the selectivity it refers to the relative retention of 2 components in HPR. That means in, let's say if we are calculating the selectivity for 1 and 2, then we are considering that how is the relative position in the chromatogram, which is calculated by calculating the capacity factor of 2, which always go as numerator, and divided by the capacity factor of the earlier peak, which was the denominator. If you calculate and put the values for these capacity factors and ultimately get onto this expression. And for 2 peaks, if they are appearing at the same time, capacity factors would be less than 1. And for the 2 separated peaks, the capacity factor is always more than 1. And selectivity is the only parameter which you are trying to adjust, because most time you are struggling only to separate the 2 merging peaks. And there are 3 parameters which are largely responsible for calculating or getting you the right kind of selectivity. That's the mobile phase composition, column chemistry, pH, and here I give you some slides. For example, in the upper chromatogram, you have 40% esternitrile in water and the lower one 50% methanol in water. And if you see the peak 2 and 3, 4 and 5, what happens? With 40% esternitrile, there is a good selectivity for peak 2 and 3, but the 4 and 5, you don't have the selectivity. And 50% methanol you have for 4 and 5, but then you lose 2 and 3, they merge. So Yeah, this is the trick now, how to go around and how to get all the 4 separated. And where you tend to adjust the strength of the acetylnitrile and you wish to use the methanol, and you get onto a combination where all the peaks are separated. And there's still another where you have 100% acetylnitrile, see the chromatogram, and if you follow these arrows, you will see that this 10 and 11, which is very well separated here, with acetylnitrile, methanol 50-50, what is the happening to this 10 and 11? And with 100% methanol, the two have merged. So that means since most of the time we are using reverse phase columns, and in reverse phase columns, acetylnitrile, methanol are the 2 most frequently used modifiers in water, and we don't very commonly use tetrahydrofuran. So you are always struggling to get the right kind of selectivity. And then other than that, we have the column temperature, which is also operative. On the left-hand side, you have a better resolution of these peaks. If you see on the right-hand side, which is at a elevated temperature. Then pH, because the molecule interact with the stationary phase in unionized form. For example, acetyl salicylic acid is the peak number 3. So if you are using pH of 2.7, that means you are suppressing the ionization of this molecule, and it is well retained. But in lower, it's the neutral pH where it is ionized, and you do not have good retention of this molecule. So this 3 becomes the first peak in the low portion, which is done at pH 7. It is not only this, even small changes. For example, propranolol, ibuprofen, you see the difference at 7, 7.25. So 6 and 7, they are separated, and these 2 merge at pH difference of 0.25 units. And then this shows the pK of ibuprofen is 4.4. If you do the analysis near to the pK pH values 4.4, you will have the tailing of the molecule with some of the molecules ionized in this form, whereas suppressing the ionization, you will have a narrow peak. Then the last, the third factor is the efficiency, which is in modern machines, you have the auto calculation of this efficiency, which for each peak will give you the efficiency. And in the same chromatogram, the efficiency for each peak is different. It is not that it's something that for one chromatogram, all the peaks have the same efficiency. So this efficiency is per peak, and it is calculated by the formula here, which takes into consideration the retention time and the base of the peak. To tell you in simple words, narrower is the peak, better is the efficiency. And since most peaks or most component, if they spend longer time in the column, they come very late and they intend to diffuse, and you are always compensating for that. So the higher value will tend to adjust. It's a kind of adjustment. And in the chromatogram, if you see the peaks onto the left-hand side and onto the right-hand side, you will always find that the left-hand side peaks are narrower, sharper. So it is not to be assumed that they are always with the better efficiency or better plate count. It is inherent property also that those escaping the column very fast, they do not get the chance to diffuse, as is those molecules which spend more time into the column. Then since this is another problematic issue, where we are not getting the desired kind of plate count and your peaks are broader, and if I have to compare it with the TLC, that your spots are not very sharp and intense. They are more diffuse, which is not the right TLC spectrum. So in case of HPLC, it is the narrower and sharper peaks which are preferred, not the broader peaks. And this broadening happens because of these three parameters, which we say eddies diffusion, longitudinal diffusion, and mass transfer. And except for eddies diffusion, the other two, longitudinal diffusion and mass transfer, they are related to the velocity of the mobile phase. This is for the eddies diffusion. On left hand side, if both the molecules reach the at one time, you have sharp peak. And let's assume they pass through this column and followed the different paths. So obviously green one following a shorter path and reaching the column for reaching the detector faster than the red molecule. So you have the auto broadening of the peak. So this is because of the packing structure of the column. So this has nothing to do with the velocity. So if your beads that you have packed, they are uniformly packed, then they will be providing more or less similar path for all the molecules. And longitudinal diffusion is, if you see, this is a strip which I have taken from TLC just to indicate that if you have a concentrated band like this, there is a automatic, a kind of phenomena where the molecules tend to diffuse from higher concentration to the lower concentration. And you will find that this diffuses on either side. Now to suppress this diffusion, if you keep your mobile phase velocity higher, this diffusion is some way retarded. And this was a again video which I will play, and you will let me play this video. Okay, so indicate that if you, if all the molecules, they are not getting the chance to interact with the stationary phase, but your velocity was so high that they did not get the chance to interact with the stationary phase, then some of the molecule will move ahead, and that is what is causing the diffusion. On the other hand, if you give it a longer time in the stationary phase, and this time is so long that from higher concentration, they are automatically fusing to this side. So here you have to maintain higher velocity. But in case of mass transfer, this velocity should not be so high that you are taking away the chance of the molecule to interact with the stationary phase. So you have to strike the balance between the two. And that is beautifully explained when this Van Demeter equation, where the broad broadening is related to all the three phenomena. And as you say, the H, which is height equivalent to theoretical plate, we say that smaller is H, better is the efficiency, less would be the diffusion. That means you will tend to keep the H value to the minimum. Now, to keep this minimum, it takes into consideration the values coming from those three kinds of diffusions. That is diffusion A, where you cannot do anything, only the morphology, packing, all that makes the difference. And then B, where you were, this was this where the auto diffusion from higher concentration to lower concentration, increasing the velocity, you are reducing it. That means you are reducing the value of B by increasing the velocity. And then mass transfer, where you are increasing the diffusion by increasing the velocity, because you have taken the velocity to an extent where it is not allowing the chance for all molecules to interact with the stationary. So the sum of that, and this now shows that if you are using different size of particles, 10 micron with 1.7 micron, then the lowest value for 10 is only probably in a very narrow range. So if you decrease the velocity of mobile phase less than that value or more than that value, that is this top curve where it is nearest to the x-axis. So that's the point where you have the optimal velocity. Whereas when you reduce it to 1.7 micron particles, you have a very large range of velocity that can be employed for with not so much compromise of H value. Again, with 3.5, 2.5, 1.7 micron, you have 20-minute run, 10-minute run, and 2.2. So the same kind of chromatogram which I showed you earlier. So this 30-minute chromatogram you are completing in 5 minutes, and that is too with better efficiency. So then last is resolution, which is a measure of how well the two components are separated. It is expressed by this difference of retention time between the two and divided by the average of the base of these peaks. So this difference in the retention time divided by the average base of these peaks is what gives you the resolution. Obviously, if you have resolution value of more than 1.5, then peaks are completely separated. In lesser value of this resolution, you have the overlapping of the peaks, and we have the compromise of the analysis when these peaks, they merge at the or overlap at the bottom. And this resolution is related to all the parameters that we studied: capacity factor, selectivity, and efficiency. There's a mathematical calculation also, but I will explain in simple words that how these parameters they influence. The column efficiency, we can increase the column length, we can reduce the particle size. For selectivity, we adjust this appropriate stationary phase, mobile phase, that triangle which I showed you, along with the pH. And the retention factor is obviously again by decreasing strength in mobile phase, you will increase the retention time. And here is a image which I have taken from Agilent Technologies. It beautifully explains that how it happens. There, for example, this is a situation where the two peaks are not resolved. So what can you do? And for example, if you take into consideration the capacity factor, if these peaks were appearing at this retention time, if you further reduce the retention time, you'll see further overlapping of the peaks. But if you increase their retention, you will have some resolution of these peaks. That means capacity factor, how it influences the separation of these two peaks. Then is the selectivity, which where it's the comparative retention of the two. What did you do? You did not do anything for the first peak, but for the second peak, you increase the retention. So you adjusted your stationary or mobile phase composition such that one of the component achieved better selectivity. So you could achieve the separation. And in the last scenario, for example, you have not done anything, you have only increased the efficiency. That means you have increased the plate count and you have made these peaks much narrower. So in the same retention time window, you are able to adjust these two peaks and still you had the resolution. This is how the factor, selectivity and efficiency, they help you to improve the resolution. And the asymmetry factor, the tailing factor, which is although not out of those 4 factors, this is one of the parameters which is normally taken into consideration. And we expect that peak should be symmetrically distributed on the 2 sides of this perpendicular drawn from the top of the peak to the bottom, but it normally is very difficult to attain. So if the base is asymmetrical, that means you have more of A than B, you have fronting. If you have more of B than A, you have tailing. And tailing is a normal problem that we encounter. And this tailing or asymmetry, for example, these 2 parameters that practically referring to the same. Asymmetry factor is calculated by dividing this B by A at 10% height of the peak. Whereas tailing factor is at 5% of the peak, and this is A plus B divided by 2A. And USP has given the tailing factor of 0.5 to 2. And this cannot in the chromatogram. So this was basic about the chromatogram, and then I quickly tell you something about the applications and the analysis. Now, whenever you are doing the HPLC, it's very important that what are your goals. And in one case, for example, you may be going for the quantification, let's say, of one marker component in a plant or in a formulation. In that case, you don't need to resolve all the components. Other instance, you might be working for generating a good fingerprint where you are interested in resolving all the components present in. So this should be very clear that what for you are using the HPLC. Then accuracy and precision features which we all are aware of, and what are the requirements of the regulatory agencies or of your suppliers or of whom you are submitting your data, and accordingly you have to work. And then the analysis which you are carrying out is whether the plant material or it's a finished product, or you are also using it for biological samples. So how many different matrices you are coming across. So for example, if you are carrying out the marker analysis and you do it for the marker, you get a very good capacity factor, very good efficiency, and when you transfer it to the analysis in the plant material, you find there is another peak appearing below this peak. So your whole effort is gone away. So that way you have to be very cautious of knowing that how many different matrices you would be working for the analysis of the material. And then it's more important to know that how many samples you will be handling. But if you have few samples, you can have a longer run time, you can run the gradient, and you can run the analysis of in 60 minutes. For example, you have thousands of samples, you cannot afford to have a gradient for 60 minutes, and you have to find out something very quick working situation. And then last, what is available in your laboratory, one should try to make use of that rather than always grumbling that we are not having this, we are not having this. And HPLC can be used for separation of all phytochemical compounds that are not volatile, and for volatile compounds, this is the better option. And beside analysis, we can use the HPLC for identification of components from the retention times, like we do in TLC by comparing their RF values. And then we can have the quantitative estimation of analytes. Then it's possible to study components using the semi-prep machines or preparative scale HPLC systems. And in markers, it can be single marker analysis, multiple marker analysis. When you are using multiple marker analysis, one should consider developing the standard plots by using a mixture of markers rather than making the standard plots with each marker and then using that standard plot for the multiple marker analysis. And before you actually develop the standard plot, one must see that whether you are able to resolve those markers in the plant material or in the formulation or not. Then isocratic mode, where you do not change the composition of the mobile phase during the analysis, is always required. But if it's not able to serve your purpose, you shift to the gradient mode, where you have more capabilities and widely different ingredient can be adjusted in the same run. So, but gradient mode is always difficult and it should not be the first choice. Then this point, last one I already told you. Then this is something which I would like to share with all the audience, that many times we do not have the standards for the markers, and we always struggle that what to do in such situation. My advice always in these cases is that in most cases we are only comparing the quality of plant material or quality of the formulations, where you can consider comparing the peak areas. And here the only thing that you have to do is that you have to identify the peak. That, okay, let's say if you are seeing glycyrrhizin and glycyrrhiza extract, then you should only be able to see that which peak corresponds to glycyrrhizin, where HPLC or LC link to mass can help you, and you can get to know, or from literature you can get to know. And then in the absence of analysis, at least you can compare the comparative rating of different samples or comparative rating of different formulations. And then this point is because we are not so interested in absolute value. We are always interested in analyzing different samples and how the analyte composition varies these. Then other than this analysis of markers, single marker or multiple markers, we use the HPLC for generating fingerprints, where you have very large capability of this tool, and you can vary the stationary phases, we can vary the mobile phases, you can use isocratic, you can use gradient, and you can generate endless number of fingerprints, and you can select good fingerprints out of them. Or in another cases, we can use a number of different fingerprints for evaluation of plant material. So here the first step is that you generate a good fingerprint, either one or different kind of fingerprints using different conditions. Then this data, if it's a small data, you can obviously visualize it and compare this either raw or after some treatment where you adjust the rather than use the relative retention times or other kind of adjustment that you give to the data. Then analysis, as I told you, either visual examination, which is very subjective and it cannot be exact. Then the objective examination is possible manually also by assigning values, which I will shortly explain. And here you can give the weightage, or you can use unweighted fingerprint. That means if let's say in glycyrrhiza, you are calculating, you know that glycyrrhizin is important constituent. So the peak of glycyrrhizin can be given the higher weightage in comparison to the other peaks, but you tend to compare the entire chromatogram and entire fingerprint. You can use ingenious method, which I will explain how you can use these softwares. For example, this I'm giving you the ingenious method that in one example, the industry approached us and they wanted to see that whether Prunus domestica, which is growing in our country, can be substituted for Prunus africana, which is used as a drug for BPH, and it's coming from Africa, and it's a very popular medicine in Europe and in US. So what we did, we in fact did an exercise where we had a large number of Prunus species, all of them are listed in the top columns. And on the left, we have the retention time. And we noted the AUC in lakhs.
It should come in a single page.
And say, so you have retention time up to 28.4. So in all, we had 30 peaks, which were observed in Prunus africana. And we made a scale on 60. And we assigned 1 mark for peak presence or absence. So if there is a peak corresponding to Prunus africana presence in domestica, we will give it 1 mark, and if it's not there, we will give a 0 mark. And then half of the marks we assign to the peak areas, where we gave 1 mark for peak AUC if it is equivalent to the peak area or more than the peak area present in the true drug, and we calculated it proportionately if it was less than Prunus africana. And here we showed that the Prunus domestica, which it had 54 marks out of 60. Of course, 60 would have been that exactly the same as africana. So we showed it that Prunus africana is very similar to Prunus domestica. And in fact, the industry continued the project, and they have got the patent also, and they are selling the Prunus domestica now for substituted for Prunus africana. Now the same, we also subsequently we procured a software, and we used that software set number for carrying out the analysis, where we calculated the similarity analysis. So here you get the values, and it actually gives you that which species is how much similar to the another species. So you can have the analysis for all these species, and you can see that, for example, we take domestica. So you have 0.773 as correlation of coefficient with Prunus africana. And in this analysis, Armenica was probably the most, followed by Cerassoides, and then was the domestica. But domestica is one which is very, and we commonly call it as Adus. This is available. At one time we carry out the pruning of the trees, and the bark is available. So the company was very happy to use the bark of domestica for Africa. So that is using the HPLC for developing the fingerprints and comparing the fingerprints either visually or using the special statistical tools or the softwares. So that is all which I wanted to share, and I still feel that science, especially in pharma, without HPLC understand, does not stand any chance. Thank you very much.
Thank you, sir. Am I audible?
Yes, sir.
Yes.
Thank you.
Yes,
Thank
Raju,
you,
you are audible.
I thoroughly enjoyed your talk, and you have covered all the aspects: injector, column, detectors, types of chemistries, column chemistries, even column and particle size, mobile phases, how we can evaluate the chromatogram, and the most beautiful part that you have included, that those pictures, those videos, and I must appreciate that it is wonderful presentation. And at the last you have covered this marker analysis and fingerprint analysis, sir. Sir, I request all the participants, please give a big round of applause for Dr. Karan Vasist. Thank you very much, sir. It was a great pleasure to listen your lecture on a very important topic, that is HPLC. And I feel all of us are fortunate to have you as a speaker on this thoughtful topic. Thank you very much, sir. With these words,
thank you so much.
Pathak sir, if you want to say something, please.
Thank you, sir. Thank you very much.
Thank you, sir. Anyone if has
yes, any participant,
most welcome now and afterwards. You can share my email, and if someone has any issue with the HPLC analysis and the little knowledge that we have, we can always help them.
Right, sir. Thank you very much, sir.
Thank you for your generosity and
certificate, sir. Bodla, sir, we are going to present. Please, please share the certificate. Dr. Mahavir, you want to say something? Dr. Mahavir.
Yeah, sir. Good afternoon. Good afternoon, sir.
Yeah, please.
Good afternoon, Mahavir.
Yeah, sir. Actually, I am very lucky. I did my PhD under your supervision, and I learned so many things from you. And I'm trying to implement these things in my life, especially in the career life. Not only the scientific knowledge, I learned also the behavior, humanity, and everything from you. Hard work, dedication, and many things, sir, in the administrative side. Thank you very much, sir, for the guiding during my PhD, sir.
I must share my good days with Dr. Pathak, and when Dr. Pathak and myself, we were pursuing our PhD degree, and those days and that little time when we used to chat is so remembered, that you always feel like going back to those days and that time. It was very wonderful time. We always miss in our life those days.
So is here, sir.
So from participant side, if they want to ask any question, please, they can ask question.
Related to HPLC,
I think all of them are satisfied. Yes, please, sir.
We find it so interesting that you are delivering lectures sitting in front of laptop, and when we take class from our room, I often feel that how students must be feeling at this moment. Then I tend to remember my days, that what we were as students.
Yes, sir, you are absolutely right. And I can say that the topic you have covered, it's not easy to cover within 1 hour. It took 3 to 4 hours. Right. And you did it, sir. It's a great, you did it very well.
Good evening, sir.
It's a beauty of your lecture, sir.
Mahavir, you want to say something?
Good evening, sir. Hello.
Please.
Dr. Satish.
Sir, I am Dr. Satish. Sir,
yes.
Actually, I have a doubt, sir, actually.
Right.
In HPLC, the separations and all, so what about the chiral molecules? How to identify the chiral molecules, sir? And the selection of solvent system, how to do the selection of solvent system for chiral molecules, sir?
Chiral molecules, okay. Sir, please.
Unfortunately, with chiral chemistries, I have not worked, but all manufacturers, they are supplying you chiral columns. And what I request you is that if you go to the site of Waters or of Zealand, they have a beautiful depiction of all kind of chiral columns that are available with them. And not only that, they have given few days back only I was saying, they have given enough information with respect to selection of the solvents also. So I would request you to go to the site of Waters, or in the net also you can search chiral columns, Waters chiral columns. Probably it will take you to those presentations which are specially onto the chiral columns use. And there, I'm sure that you will get answer to all your queries there. But personally, I have never worked with the chiral column, so I feel handicapped in answering your particular specific queries.
Thank you, sir.
Right.
Thank you, sir. Thank you.
Dr. Bodla, you want to
Yes.
say something, please,
Sir,
on this question? Yes.
it was very exciting to listen to you, and in fact, we were forgetting ourselves as faculties, and we were just listening like a student. And sometimes it gives a great feeling to become a student in front of a teacher like you.
No,
And
it's
and
it's your.
whatever we have studied at our fourth year BPharm level and MPharm level, you have just encapsulated very simply and so elaborately. This just penetrated and percolated into our brains, and it has stimulated our immunity. Yes, yes, we studied this thing. Yes, yes, we were not knowing this particular thing. So that is the way of your teaching, sir. It's a very tremendously, very impressive and a nice lecture and a nice presentation. As Dr. Raju said, it is a very meticulously framed and prepared lecture.
Thank you so much. And in fact, I would like to share that why we have this kind of information, because we probably were the first in this northern side to buy the HPLC machine of Waters.
Okay.
That was in 1986.
Okay.
And probably till 3-4 years back, we were using that HPLC machine.
Same HPLC, sir.
And the all components in those days, you used to see what is happening, and it was modular kind of system. You actually see the functioning of the pumps also. You know that how to tighten the rules, what is the role of rules. I mean, those little things, and that time we were using the thermal paper for taking the chromatogram,
Right.
giving you a analysis. Then we were struck up because the thermal had got destroyed and there was no replacement. Then we bought software from the open market. So we had been evolving as the HPLC was evolving. So when we see the modern machine, we get amazed that look how simple it is, and it's convenient to time to do everything, which was so difficult in our time. So that's probably the reason. And then I always tell the student that probably the most information can be taken from the site of the manufacturers, because all these manufacturers, good ones, they have beautiful PPTs. They explain all the points. Even, for example, if you want to see for the method development, you will have slides from Waters, from Aziland, from Schmarzu, from Thermo. You can spend days going through those presentations and keep yourself that what can be done. And as you go through this literature, you automatically feel more educated, you get more capabilities, and you are in a better situation to handle the problems also.
Thank you, sir.
Thank you, and I'm really obliged for all your good comments.
Thank you, sir.
Thank you, sir. Thank you. I have a few lines for you, sir, for both of you. If you agree, I want to say something.
Yes, yes, please.
Sir,
Please,
communication,
please.
there is no doubt, being a teacher, the communication is a very strong thing that if we are not able to communicate with our students, then all these technologies and the means are waste. Even we can see that in the offline classes and online classes, but we are observing that if we are not able to see the faces or the expression of the students, that means we are not satisfying the needs of, we can say, the basic needs of students and even ourselves also. So कहते हैं लफ्जों में भी जान होती है, लफ्जों में भी जान होती है, इन्हीं से दुआ इन्हीं से अजान होती है। दिल की गहराई, ये दिल की गहराई के वो मोती है जिनसे व्यक्ति की पहचान होती है। तो सर, फॉर बोथ ऑफ यू, प्लीज गिव बिग राउंड ऑफ अप्लॉज. So it was a complete package from ma'am and you on the SPLC. It was a complete package for all of us, all the participants. The introduction given by the ma'am and the fundamental part and the other aspects of the SPLC you have covered. Very wonderful.
Sir, in fact, I am really surprised. You are together learning and together solving each other problem, and together executing your SPLCs and sailing in the same boat for the even in the professional life. This gives us a great feeling. At least we have a couple now we call them as Cognicy couple.
Best example, sir, for all the pharmacists.
Cognicy couple of India.
Thank you.
Thank you, sir.
Thank you.
Manju madam.
Thank you, sir. I want to thank you, sir, for excellent lecture. इतना simple lecture दिया सर आपने, very extensive lecture, and explained very simple way.
हमें लगता है कि हमने जो कुछ सीखा इतने सालों में वो बाकियों के साथ शेयर कर लें तो प्रोबेबली अच्छा है।
सच में सर बहुत अच्छा लगा आपको।
बहुत अच्छा थॉट है सर, बहुत अच्छा थॉट है।
Very much delighted, sir.
Yes.
Very much delighted. Now I request our Pathak sir to present e-certificate, sir.
Pathak sir, please.
Pathak sir.
Please share that certificate on screen. No, please share that certificate on screen.
Oh, just wait. I think.
Yes,
yes. Sir, thank you. Please accept this certificate, sir.
Thank you, Dr. Pathak. Thank you.
So kind of you.
Thank you so much.
Thank you, sir, for being with us.
Thank you, ma'am. Thank you, sir.
Thank you very much, sir.
Thank you.
Yes, sir.
Thank you.
Thank you.
For participants, now there is announcement. Tomorrow morning we will be joining at 9:15 a.m. For tomorrow's session, we are joining at 9:15 a.m. So you join 5-10 minutes before the commencement of lecture. Okay? Now goodbye to all participants. Have a nice time.
And goodbye to me also, ma'am.
Oh, I forgot. Thank you very much, our chairperson.
Ma'am, 2 hours I spent today because of you only.
Yes. Thank you very much.
It was a wonderful experience for me also as a chairperson, and very well organized. And thank you very much for giving me this opportunity to listen the lectures without work. That I can say.
राजीव सर को 2 घंटे की जगह पे बैठा के रखना वो भी बहुत इम्पोर्टेंट काम है, मैडम ने ये कर दिया है।
चलिए, thank you very much, Dr. Rajeev.
Thank you.
Well coordinated. Thank you, Dr.
Best wishes, ma'am, for the days. My best wishes are with you.
Thank you, Dr. Rajeev.
To all the participants.
Okay, goodbye to all.
Goodbye.
Thank you.
Take care.